Alright, we're in the fourth video in chapter 8, and we're actually in the middle of the third video. We were starting to talk about types of chemical reactions. There were four basic categories, if you have any chemical reaction in this class, that you could place those chemical reactions in. And within those reactions, there's also other levels or subdivisions or subcategories. Like some of you have probably heard of redox reactions, and those can fit into different categories as well. But those four categories were combination reactions, decomposition reactions, single displacement reactions, and double displacement reactions. And in this video, we're going to talk about single displacement and double displacement reactions in a little bit more detail than we did with the others. Because on these reactions, I want you to not only be able to, if I give you a reaction, to be able to tell me what type of reaction or category it belongs to. Like, oh, this is a single replacement reaction. But I also want you to be able to, if I give you the reactants and tell you it's a single displacement, could you predict the products and balance the equation? So that's what we're going to be doing in this video, showing you how to complete a reaction. So first let's talk about single displacements in a little bit more detail. We said a single displacement reaction occurred if you have an element that reacts with a compound. If you have a single displacement reaction, that element will switch places with one of the elements in the compound, and it will give you new products. So you'll have a new element plus a new compound, AC. We said that A, depending on what A is, it turns out, can either react with B or it can react with C. It can switch places. So we could also get the new element C plus BA. How do we know which reaction is going to take place? Down here, for single displacement reactions, I've got two different types. It turns out that A is always going to be an element, and BC is going to be an ionic compound. So what is an ionic compound? An ionic compound always contains a metal and a nonmetal. So BC is always going to be ionic. B will be the metal cation, and C will be the nonmetal anion, and whatever their charges are. Because they could not only have a +1 charge, but maybe a +2 or a +3, -1, -2, -3. So an ionic compound is always a charged compound. The ions have charges, and overall it's neutral. When these reactions take place, by the way, an ionic compound is always a solid. Solids, remember, all the way back to chapter 1, those particles in a solid are stationary, they don't move. So in order to get the displacement or the rearrangement of an atom into a compound to switch places, we've got to make the ions inside the ionic compound mobile. The way the chemists do this is they dissolve it in a solvent, like water. So remember the AQ meant aqueous? If you dissolve an ionic compound in water, basically what you do is you break the ionic compound apart. It dissociates is the word. Not disassociates, but dissociates. For example, if you have sodium chloride, we know sodium chloride is table salt. It's a solid. The sodium and the chloride aren't moving around. They're literally stuck together, right? Those Coulombic forces of attraction. We know we have sodium cations and chloride anions. What happens, though, is if we dissolve the sodium chloride in water, we know that it will form an aqueous solution, which means it is soluble in water. When you dissolve salt in water, you get salt water, right? Salt water is really the dissociation of the salt and redistribution inside of the water. So the sodium ions will break free of the chloride ions. Now, why is that important? When they break free of one another, and you've got water molecules in between them, inside of your mixture, the sodium becomes liquid-like, and the chloride becomes liquid-like as well. And we know liquid particles move around. So they become liquid-like, they become part of the solution, or mobilizing around. Now you can see how A and B can switch places. So, oops. So what we have here is, in single displacement reactions, you're always going to have an element reacting with an aqueous ionic compound. And something will switch places. Now, which one will A switch with? How are we going to know if it switches with the metal, the cation, or the nonmetal, the anion, in the compound? Well, it depends on the identity of A. If A is a metal, it's going to replace the cation, or the metal, in the ionic compound. So metals always replace the cations. All right? And if you have a nonmetal, we know nonmetals form anions, so they will always replace the anion in the reaction. So depending on what A is, that's what it will replace. Here's some examples. You have a zinc plus hydrochloric acid, which we know is H plus Cl minus. It's aqueous, it's dissolved in water. All right, so zinc is a metal. It's a transition metal. Zinc then will form a cation for the single displacement reaction. It will switch places with the hydrogen. The metal switches places with the cation, okay? The nonmetal switches places with the anion. All right, now, what else? Do these reactions always occur? The answer is going to be no. If you take any metal and put it in HCl, sometimes the metal will react with HCl and you'll get a displacement reaction, and sometimes the metal will not. How do you know if it will occur or not? Well, in order for the metal to undergo the reaction with the ionic compound, the metal has to be more active than the cation. Now, what does active mean? We'll talk more about activity when we talk about redox later on, but basically, active means, for a metal, means more able to lose its electrons. All right? So, or more able to become a cation. Zinc is more active than hydrogen. Now, how do I know this? Well, chemists have performed many experiments and done many measurements, and they've come up with something called an activity series. And on the test, I will give you an activity series. So you'll always have an activity series for this class. You won't have to memorize it. Now, when you get to higher chemistries, after you understand these reactions, they'll probably ask you to memorize the activity series so you can predict reactions out of your head. But for the time being, I will give you this activity series on the test. Now, the activity series, and this isn't a complete list, but it's just a list of metals and how active they are. Notice the arrows going this way in our activity series. On the bottom, in this series, we have the least active metals. And at the top, we have the most active metals, the ones that are most readily become cations or lose their electrons. In the middle here, we have hydrogen. I always use hydrogen as kind of like, where's hydrogen? Because hydrogen is not technically a metal, but it forms cations. So it kind of acts like a metal sometimes. So we have this increasing. Now, if we looked at this reaction and I asked you to predict whether or not zinc would replace hydrogen in this chemical reaction, you would say, let me check the activity series. The question you would ask is zinc more active than hydrogen? Is zinc more active than hydrogen? So here's zinc on the periodic table, and here's hydrogen. Zinc is higher up than hydrogen on the periodic table, on the activity series. I'm sorry, I don't know why I said periodic table. Let me start again. Zinc is more active than hydrogen on the activity series. So we would say that zinc would replace hydrogen. If the metal is more active than the cation, it will replace it, because it means it's more able to become a cation. All right. So because zinc is more active, we say, yay, it wins out. Because zinc is more active than hydrogen, yes, it will replace. So what do we do when we say it will replace something? Well, we're going to be able to predict the products. So if I said zinc definitely was more active than hydrogen in HCl, which was aqueous, so here we throw some zinc metal into hydrochloric acid, are we going to get a chemical reaction? Absolutely. And you can predict this without going to the lab. And then you can test it, go into a lab. You can take zinc metal and throw it in HCl, and I promise you'll see bubbles. How do I know you'll see bubbles? Well, we're going to take zinc and hydrogen, and we're going to do the double or the single replacement reaction. The hydrogen, which is the cation, and chloride's the anion, will replace. So hydrogen is going to become the neutral element of the metal, and zinc will become the cation. So what is the neutral element of hydrogen? Is it H? No, it's H2. Hydrogen is a neutral element, is H2. And we know it's a gas. This is where the bubbles are going to come from. So this reaction is going to produce hydrogen gas, or it's going to bubble. All right, so hydrogen is the element that comes out when we switch places. What will be the ionic compound that's produced? Well, we know it's going to be zinc and chlorine, zinc chloride. Now, when zinc becomes a cation, what charge does it possess? When zinc becomes a cation, remember the backwards periodic table, the back of the L on our periodic table that we had? When we were in the transition metals, oops, I guess I drew that wrong. Do you remember that zinc had a +2 charge? Because zinc was one of the 3 transition metals that only had 1 charge. So zinc's charge is always +2. So when we ionize this, we have to rebalance the charges in the formula. So zinc's +2, chlorine is chloride, it's -1. So when we go to write that compound, zinc is +2, chloride is -1, we're going to have to balance the formula. Do you remember how we did that? We need 2 chlorides for every 1 zinc, so the +2 charge is balanced with the -2. So when we write zinc chloride, we're going to write ZnCl2. Now this is the main part of the reaction I promise most people will miss. They will forget to balance the ionic formula for the new ionic compound that's produced. But we're going to form ZnCl2, aqueous, dissolved in water. Alright, or maybe actually not. But we're going to form this compound. Oops, I erased my 2. There we go. Alright, now, this is the reaction that we're going to propose happens. Zinc plus hydrochloric acid will produce hydrogen gas and zinc chloride. Now, the question is this equation balanced? Every time you ever write a chemical equation, and here we just predicted the products, we have to balance the equation. So we've got zinc. We've got 1 zinc on this side. We've got 1 zinc on that side. The zincs are balanced. How many hydrogens do we have? We've got 1 hydrogen on the reactant side. Ooh, we have 2 hydrogens on the product side. So what are we going to do? We're going to put a coefficient of 2 in front of the HCl. So now we have 2 hydrogens. So our zinc's balanced, our hydrogen's balanced. The third element we have is chlorine. We have 2 times 1 chlorine, and we have 2 chlorines. So now the reaction's balanced. So the full chemical reaction, if I asked you, would a single replacement reaction occur if you mix zinc with the hydrochloric acid? The first thing you would do is you would say, is zinc more active than hydrogen? You look at the activity series. If it's more active, it will react. It will form products. The products will be hydrogen and zinc chloride. You'll have to figure out the ions that are formed, and then you balance the equation. So this is the equation that I would expect you to be able to produce. All right. Now, do reactions always occur? The answer is no. Only if the metal is more active. So now I'm going to give you an example of a time a reaction would not occur. If you have a metal and you throw it into HCl, if the metal is less active than the cation, it will not react. So here we have copper plus HCl. So copper is our metal. It's down here. And we're reacting it with HCl. So is copper more active than hydrogen? The answer is no. Copper is not more active than hydrogen, so it will not replace the hydrogen. It's got to be more active to replace. So what will happen here? What will happen is we would say there's no reaction. That's actually what we write as chemists, NR. NR means no reaction. So we don't predict products. These are always people's favorite because they don't have to balance the equations. I'm not going to lie. But actually in the lab they're the most boring, so you'd rather the reaction occur so you see something cool happen. Alright, so those are 2 examples of single displacement reactions with metals. What about the non-metals? Same exact thing, except a little different. If you have a non-metal and you mix it with an ionic compound, and you want to know if the single replacement reaction is going to happen, If A is a nonmetal, it will replace the anion in the ionic compound. So how do we know if it will replace or not? If the nonmetal is more active than the anion, it will replace it. But if it's less active, then it will not replace. So how are we going to know if it's more or less active? We're going to look at our activity series. And remember, again, I'll give you the activity series. So let's look at the activity series here. For this reaction, it says fluorine plus sodium chloride. So first of all, we say, well, fluorine's a nonmetal. So if it would react, it would replace the chlorine in this reaction. So we're going to compare the activity of fluorine with chlorine. Now, fluorine is more active than chlorine, so it will replace. So in this chemical reaction, notice we've predicted products. Fluorine will replace chlorine because it's more active and will produce products. Now, what will the products be that we'll produce? Well, let's come down here and see. I don't want you to look at the answer. I want you to be able to predict it. So we've got fluorine, which is diatomic element, plus sodium chloride. Oops, I don't know why I did that. All right. The question is, will it react? We said it would react because fluorine's more active, so it will replace the chlorine. So that means the chlorine is going to come out, and it's going to be the element. Remember, the element chlorine is diatomic, so it'll be Cl2. So that's our element. And our compound that's going to be produced is sodium fluoride. Now, here's what you don't do. You don't write NaF2. 80% of the time, my students write NaF2, and they get it wrong. I don't want them to get it wrong. It's not like it's a trick question. They just don't think about what they're doing. If you understand what's happening here, you're producing an ionic compound, sodium fluoride. How would you write sodium fluoride? Well, sodium fluoride contains a metal and a nonmetal, so it's ionic. So you're going to have to balance charges of ions. Sodium has a +1 charge. What charge does fluoride have? Well, it's in group 7 on the periodic table, 7 minus 8, -1. So here we have a +1, -1 charge, right? So do we need to add any subscripts to balance the formula? No. Sodium fluoride is NaF. So that would be our new compound produced. Okay, now is the equation balanced? Absolutely not. Okay, so we're going to balance the equation. Now we've predicted the products. I'll always tell you, predict the products, and if the reaction occurs, balance the equation. So obviously it occurred. Fluorine is more active, so now we're going to balance the equation. We have 2 fluorines on the left, but we only have 1 fluorine on the right. We need 2 fluorines on the right. Remember, always balance up. So how am I going to balance the right-hand side up? Well, I'm going to put a coefficient of 2 in front of the sodium fluoride. So now I've got 2 fluorines and 2 fluorines. Fluorine's balanced. Let's go to sodium. I've got 1 sodium on the left, and I've got how many sodiums on the right now? Oh, I have 2 now, because I have a coefficient of 2 times 1 in front. Remember to always balance up. So that 2 on the left-hand side, I'm going to have to put a 2 there. And now I've got 2 sodiums. So now my sodiums are balanced. Let's look at the chlorines. How many chlorines do we have on the left? Don't say 1, because we have 1 times 2. Be careful. We have 2. And then how many on the right? We have 2. So now the chlorines are balanced. So this would be the equation you would predict if I asked, does fluorine react with sodium chloride? You would say yes, it does, because it's more active. And when it reacts, it will form chlorine plus 2 sodium fluorides. All right, so that is how you do single replacement reactions. Go ahead and practice those on your own and see if you can predict the products, balance the ionic formulas, and if a reaction occurs, balance the equation. If there's no reaction, write no reaction.